or quasi-non-expansive mappings to this larger class of demi-contractive mappings. I forgot to say something very important. This is not exactly the situation. So non-expansive have in common non-expansive are not included completely in quasi-non-expansive, but if T is non-expansive and fixed point of T is non-empty, then T is quasi-non-expansive. So here, all mappings which are here non-expansive have fixed point of T non-empty. We are interested only in non-expansive mappings which have a fixed point. So, in fact, our approach is to extend all results for non-expansive mappings or from quasi-non-expansive mappings to the larger class of demi-contractive mappings. And also, as it is normal to such kind of approaches, I present some examples to illustrate the effectiveness of our analytical results and also the superiority of our algorithm over the previous ones. Here, I also insist that we extend all non-expansive mappings which have fixed points are here. So we extend all these, the results for this kind of mappings to the green area, so to a larger, very large class of mappings. I again insist on the fact that demi-contractive mappings are till now the largest class of non-expansive type mappings for which we can approximate the fixed points. So this is very important. In concrete applications, we need classes of mappings for which we can construct the fixed points. So in Nash equilibrium problems, for example, we use topological fixed point theorems. Here we don't have a method to construct fixed points directly from the fixed point theorem, but there exist methods to construct, to reach such fixed points. Here we have, by definition of the class of these mappings, we have a constructive algorithms. But there are many algorithms. And I present you this algorithm that I consider here. So I have a map S in that case, which is demi-contractive. We start in this way, step 1, step 2. This is what I promised. This is the inertial term, xn minus 1, sorry, here. So the previous step. So to make it inertial, is it possible? Okay. At my home university, no. Look, at my home university, I am working the same. So with such kind of blackboard of a board and this one, and sometimes I am trying to write here.
No, this is also working.
I know. I know, but on this one, when I write at home, even my clothes are writing something. Why I touch.
This is very common phenomena of many mathematics teachers.
Yes. My teacher of mathematics in high school, he was extraordinary good mathematician. He was, when we finished, he was finishing the class, he was full of chalk, yes, all the face, because he was doing this. How to solve this? And
No need of any cosmetic products. I never used in my life. This is enough for me.
Okay. Okay, let's come back. So this is the algorithm. It's inspired from the previous algorithm. Here are the elements. You can see this inertial coefficient theta n is defined in this way. We have significance for any element. Theta is a given number, and this theta n, which appears here, yes, is defined in this way. F is this contraction. So here, look, we use contractions, Banach contraction inside this algorithm. Why? Because, as I explained, this anchor, if it is a contraction instead of, let's say, G of xn, here is G or F, is G. So if we use a contraction, the algorithm will behave better because of the properties of a contraction. Now I remember the name of this mathematician who introduced, Moudafi is a French mathematician who introduced this viscosity type by putting in Halpern type algorithm contraction. Instead, any constant is a contraction because a constant map is always a contraction. So this is the algorithm, and here is the significance of this f that appears in constructing this theta n. So this is the algorithm. It looks very difficult to implement, and I'll speak in my talk about error analysis how difficult it is to implement such an algorithm. Okay, things are very nice in theory, but when I have to project something of a set, it is not easy to compute in general this projection. If the set is, let's say, a disk, then it will be nice because we have a unique projection. We can compute in the plane, for example. We have this element, and the projection on the set, let's say C, is easy to compute. We can compute analytically. But if this set is still convex, but is of this form, then it will be not so easy to compute the projection. I mean, when we are implementing it in a certain software package. So this is an algorithm which looks nice, and we'll see it converges to a solution of our split feasibility problem, but it is not easy to implement at all. It is not easy. So the main assumptions on these elements are put here. I don't insist on them. These are all needed to ensure the convergence, the strong convergence of this algorithm. Here, what is here? This shows that we have before a convex combination, 3 terms. So this expression here is a convex combination of 3 elements. Why we need such a convex combination? Because we want to be sure we do not exit the set. So because our set is convex, we know that any convex combination will stay there. We will not go outside our set.
Closed and convex.
Yes, closed and convex. So this is the moment we stop is this one. If we perform one iteration, if we reach this moment, Fn, I remind which is Fn, this is this quadratic mean. So when we have f of xn, f being this expression, the projection I minus p on q times ax, and when this is 0, that the then we have to stop, and then otherwise we continue our algorithm. This algorithm is convergent, and we can prove this convergent theorem. So our result, main result in this paper, it was published in this year in the Journal of Inequalities of Application. It's a Springer journal. Is needed to pay.
$1,600.
It's a lot of money, but fortunately my university is supporting us. So, really, if I publish 100 papers per year, they will pay for all. But I cannot. Fortunately, I write no more than 5, 6, 7 papers. But fortunately, I told you yesterday we have this policy for our university to stimulate publishing in very high ranked journals, and this is why my university is in this Shanghai ranking. We are there by mathematics. By mathematics, we are in a good position. In this classification, Shanghai ranking for subjects is based only on research, and we are here there by mathematics is the only subject we are there. And the first university from Romania in this ranking is University of Babeș-Bolyai, of course, in Cluj-Napoca, and we are on the second place. They are the 78th position, we are on the 178 or 79. This is a good position. Only 500 universities are classified here. So this is the result of the policy of our university to stimulate publishing, because you know they are interested to have high ranking from the university. It's a lot of money to publish in such a journal, but this is a Q1 journal, so this brings points in that classification. If I have time, I'll speak about this Shanghai. I do appreciate this Shanghai classification because it is.
What do you say about this? Since you're talking about in general, one more is MDPI also there from Swedish journals. So they are starting very hefty. 2200 USD.
This is good classification in the sense they consider only research. This Shanghai classification only based on research, because there are many other rankings. They consider all kind of other aspects related to students, to graduates, to faculty, and so on. But this is based only on research. So coming back. This is the main result in this paper. We have the demi-contractive mapping T. Actually, it will be S because I changed notation, and such that 1 minus S is demi-closed. I don't insist on this concept. If someone is not familiar, I can tell what is this. We have a contraction G with coefficient C, contraction coefficient C, and I suppose all the mentioned assumption on these parameters. And then, if our problem, split feasibility problem, is consistent, this means it has a solution, and it's a common solution with the fixed points of the operator T, then the sequence generated by the previous algorithm will converge to this common element of fixed point set and of the split feasibility problem defined by the set CQ, and this will also solve the mentioned variational inequality. I don't insist, but I have here the paper. I'll show you a little bit of it. The idea is that we use the lemma I mentioned. This is all. So there are many technical lemmas, but the one which is essential is this one I presented before. We have, in the case of a demi-contractive map, and we use the fact that for this lambda, T lambda is quasi-non-expansive, and we go back to a convergence result for quasi-non-expansive, and we get the proof for our general problem in the class of demi-contractive mapping. So this is the idea. What is important is to have in such a paper a proof that our result is better than the others. So here is the object which shows we met it before. This is the simplest example that shows that our result is more general than all the others results. And look, we showed that this map, this function on the real line is demi-contractive, has fixed point set, non-empty, is non-expansive. So none of the results established before for non-expansive mappings can be applied to this. Is not quasi-non-expansive. So none of the many convergence results established for quasi-non-expansive mapping can be applied here. And similarly, is not strictly pseudo-contractive, and so only our theorem can be applied to a problem which involves this operator T. So this is what is necessary to prove for a new result, that it is an effective extension, an effective generalization of the previous result. So this is all is needed, but it is also needed to discuss some numerical examples, how this algorithm behaves. So here are the comments of following the example. All results in these papers I mentioned cannot be applied to any split feasibility problem involving this map. And I did some numerical tests. To compare with the results here, I considered exactly the same problem as in the example 1 in this paper, and I want to draw your attention to this fact. So I did the numerical experiments in MATLAB, and I used Professor Murthy mentioned. So we cannot say an algorithm is good and perform well after one numerical test. It is needed to perform a lot of numerical experiments and then synthesize them and decide. It looks like it is better. We can say something like that. It looks like it is better than the other algorithms in this instance only, because we cannot say in general, this algorithm is the best. We cannot say never after numerical tests. Numerical tests are heuristics, they mean only by experiments. So I did this, I compared the results with the ones in this paper. I applied I used the same starting point, and I obtained the solution, which is this one. It's a vector in R5 after 33 iterations. And I don't know if I have here, these are the results for some, these are the components, because I took the problem in R5, So the components of our solution are this one, 5, and I started from this initial value 1, 1, 1, 1, 1, and this is the solution. The solution I mentioned after 33 iteration. Yes, this is the solution. You can see exactly this one. So this is 1 over 2, this is 1 over 4, and so on. This is 1. The last component is 1. I don't have here, but I'll open the paper. Oh, I have here. For the same problem, these results, Wang et al., look how many iterations they need. 10,000. 10,000 iterations, and the approximation was just good. But here we obtain exact solution after 33 iterations. This algorithm in this particular situation looks to be better, but once again, we cannot see it is always better than the other one. But for this problem, I took exactly the problem in this paper because I extended the results in this paper, and I wanted to compare the performances of the new algorithm to the other one. So this is a very good algorithm. So we can do a lot of tests, numerical tests, but I selected what is interested, and I did various tests, and what I concluded. Most of the assumptions on these parameters which are involved in our theorem are not necessary. They are imposed for the sake of the proof. So we need these assumptions to prove the theorem. Look, we go back. Most of these assumptions are not satisfied by the ones I used in the algorithm I use here for the to get this solution for 33 after 33 iterations. So this is an interesting fact. What does it mean? That we need these assumptions to prove the strong convergence, but however, this algorithm could converge in larger under weaker condition. And this is a serious challenge to find which of the assumptions can be dropped out. So for example, in my case, I took these values which do not satisfy these assumptions. But the secret is that I took, this is the secret, I took theta n 0. So my algorithm was not inertial. And the conclusion, at least for me, I took in another paper published recently that inertial algorithms ensure strong convergence, but for numerical test in finite dimensional spaces, the non-inertial algorithms are better. But look, here we are in a finite dimensional space. The most difficult examples, the real examples, are in infinite dimensional spaces. If we have a problem there, so there is a big difference between strong and weak convergence. So here, in a finite dimensional space, we know that weak convergence is equivalent to strong convergence. So this here is not quite relevant. So we should be careful on saying that in general, these assumptions are not necessary in this context. Also, some of these assumptions are not necessary when we are working in practical situation. Because in practical situation, real world problems, we are infinite dimensional cases. So finite dimensional in many problems. There are problems, difficult problems, where it is the case with infinite dimensional problems, but not here. So an open problem here with which I close is that we are challenged to find weaker conditions on these parameters such that we still can prove that the iterative process we introduced still converges to a common element of these two problems, a fixed point problem and the split feasibility problem. A final comment, why we have approached this problem. So if we are careful and read correctly this result, actually we find a common solution of a fixed point problem and of the split feasibility problem. Why not we directly approach to find a solution of the split feasibility problem? It's a very difficult task. There are approaches to do, but we are happy if we find a solution which is a common element to this fixed point problem. So the fixed point, these intersections reduces the solution, number of solutions, and anyway it allows us to catch a solution from here. So we are interested to catch a solution for the problem, and we can approach it by means of associating a fixed point problem to it. This fixed point problem helps to identify such a solution and to construct such a solution. And if you remember, this is also a solution of a variational inequality problem. So in this way, we actually solve a split feasibility problem, a variational inequality problem, and a fixed point problem simultaneously. But the key tool for this one is to work with a fixed point iterative scheme. So T is not, how to say, artificially put here. Its role is just to help to identify, to construct a solution of this problem. This would be all for this day. And I want just to show the paper. The paper is here. Please, please give them to all participants. Just I want to show you just a moment how it doesn't work.
I have a good number of papers of Professor Veermani also on proximity points, fuzzy, okay, and some of his paper also. So I request Professor Bende to provide me all the PDF, collected PDF
Yes.
in one folder.
For this paper, which were mentioned in my presentation, I'll try to.
Yeah, you try to either give the link on one page.
No, this is freely because this is open access,
Yes,
but it is better to have it.
To have the folder, and I will provide the all the papers in the group. Okay, so that will be. So give a this grand claps of applause to Professor Birendra. For his an excellent and perfect, I can say, the lecture of this session, and today's session is also over. Morning session, second half will start at 2:15, okay, as per schedule, because actually we can't start before. The reason is we have schedule already. So that's the reason that, of course, today is little bit earlier. In the first session, Professor P. Veeramani will speak, and two of our department faculty members, they are doing an excellent work.